Okay, lesson 10 part 2, the maths bit. In the previous lesson we looked at the force extension required practical, also known as Hooke's law. And because it's a required practical, really what it's after is your knowledge of all the different thinking scientifically skills. So moving on now, we're on to the maths bit. Now the kind of results you get is a linear directly proportional graph. So your results will be the straightest results you should ever get in an experiment. So I'm going to draw them there. I'm going to draw it to about that point. In fact, I'm going to put it in green for good, because if you don't go too far with this experiment, you don't break the spring. So I'm going to get to that point. And what we see is, at this point, we would describe this as directly proportional. Now there's two things about this, and again I've heard these been asked in exams. There's two things. One is a straight line. That's one clue that this is directly proportional. The other is it goes through the origin. So it is possible to have graphs with a straight line that are not directly proportional because they do not go through the origin. So those two. You can also have through the origin but not a straight line, like that one. So it's only this example where it is directly proportional. So that's that part. But if we kept going, we'd reach a point at which we would break it. We would reach the limit of proportionality. Now at this point, as we apply more force to it, and I'm going to stick with red for bad, we'd probably see it do this. It would go, but then it would start to move upwards. I'm just going to move my writing out of the way, put it over there. It would do this. It would start to stretch more for when you put the spring on. And it would get to the point where in the end it would probably snap. Like so. So that's our limit of proportionality. Now in describing these regions, along this line here, we have elastic deformation, where when you let go, it returns back to original shape. And that's kind of, when I'm giving out loads of them, that's what I hope I get back, a load of original shapes. But there's always a donut. And so here we have inelastic deformation. And in this case, it is permanently, I'll just put permanently changed. You ain't getting a spring back. They just go in the bin. So those are the regions for this graph. Now, onto the two equations. One of them you've come across already, and it's the elastic energy equation in topic P1, the energy section. Elastic energy. Now, the elastic energy of it is a half of the spring constant. We'll come back to what that is again in a minute. Half of the spring constant of the spring times by the extension of the spring squared. We can write it algebraically as E subscript E for elastic is equal to a half K E squared. Now, this one's a bit of a bane of my life. When you look at the letters, it happens to share the same letters as another equation in P1, which is the kinetic energy equation, which, if you remember, is a half mv squared. And so people who aren't great at revising look at this and they go, oh, there's a K and there's an E. Oh, is it this one? And it's not. It's definitely not that equation. It's just bad luck that those are the things they chose to use. Now let's get rid of those. So that's the first one. The second equation is easier, and this is specifically a P2 equation, and that is the force acting on it is the spring constant times the extension. So what we see here, and this is why linear graphs are so handy in science, is we have something of the form y equals mx. And if you remember in maths, this is the gradient. But that leaves us on to a little problem. Let's have a look. I'm going to take this equation and I'm going to plop it next to the graph I've just drawn. I'm going to get rid of all the gubbins a minute. You can rewind the video to copy those if you haven't already done so. And have a look at this. We've got a problem and it doesn't work at the moment. For this to work, for me to find the gradient of this and calculate the spring constant, I would need to take y, I would need to take the force. Unfortunately, for this graph, it's the extension at the side. So plotting it this way does not work. This is why they plot it incorrectly in the revision guide. So not many people notice, but they swap around the force and the extension like so. This is why I've hid it over here. If we now take my equation, and we go back over to here, if we take my equation now and bring it over to this side, we see that because f is the y-axis and the extension e is on the x-axis, if I now take the gradient of this, so let me draw my line again, it'll still be a straight line. What I can now do is I can now take the gradient. I can take the change in y and the change in x. So here I've got my y, here I've got my x, and so the gradient is the spring constant. So all I've done is swapped around the axes the wrong way, basically. Because remember, every experiment, the one you change goes along the bottom, the answer goes along the side. The independent, the dependent variable. We've swapped them so that this equation works nicely, and that allows us to find the gradient, which is the spring constant. So let's have a look at how this works in real life. I haven't got a calculator on me, so I'm hoping I don't set myself anything too tricky. Let's have a look. We have a mysterious object and we want to find the weight of it. So we apply our spring. We know its natural length. Natural length is 4 centimeters. We measure the total length as being, again, I'm going to cheat, make this really easy for myself, 8 centimeters. So our extension is going to be 4 centimeters. We also note the spring constant K. Now the spring constant K is really easy. It tells you how many newtons to stretch it a meter. So in this case, let's say it's 200 newtons to stretch the spring a meter. So the question we want is, what is the mysterious weight of this material, of this thing? So let's substitute in. The equation is F equals KE. We're going to put the 200 in. We're going to times it. Now, extension is in centimetres here, but for this to work, it's got to be in metres. So we're going to write 4 centimetres down. There's no metres, no tens, 4 centimetres. There it is. Okay, so 200 times 0.04. Well, 200 times 0.01 would be 2, and I've got 4 of them. So I believe this thing has a total weight of 8 newtons. And that's how you use that equation to find the weight of a mysterious object. I'm going to leave it at that point. I'm going to post some questions for later to do after this to practice. The more you do on this, the easier it gets. So have a go at them, submit them, and as always, take photographs of your work, attach it to the lesson, press submit, makes everybody happy. If you're really far behind and you feel it's too much, do something, anything. I can still mark it as done, and I'm happy. All right, take care. Any problems, give me a call. Bye.